This is the pre-recorded lecture video for the Thermodynamics of a Saturated Borax Solution lab. It is the only chemical thermodynamics lab that is included in 122. And it tends to be the one people struggle with the most. It's also one of the only ones that I actively encourage people to keep their notes and everything for after the lab is over. I've been pretty upfront about the fact that a lot of these labs don't carry over very much. This is an exception to that rule. A lot of what this lab centers around does show up again if you're taking organic or biochemistry later on. Some of these concepts do show up again. So unlike most of the labs, I do encourage people to keep these materials afterward, just in case you might need them later. The lab centers around determining whether or not a reaction of interest is spontaneous or not over a range of temperatures. In particular, the reaction, and I'm going to get to that in a second, is the dissolution of borax. And so what you are trying to do with this lab is determine whether for a variety of temperatures or a series of temperatures the reaction is spontaneous or not. Now, spontaneous here, what we mean by that is whether or not the change in the Gibbs free energy for the reaction is positive or negative. In other words, if delta G is positive or negative. If delta G is negative at a particular temperature, then the reaction is spontaneous for that temperature. If it's positive, on the other hand, then it is non-spontaneous at that temperature. So the goal here is to calculate delta G over 5 different temperatures and to look at those delta G's and see, are they positive some of the time? Are they negative some of the time? Are they negative all the time? You're really not so interested in the numbers as you are just whether or not they are greater or less than 0. There are 2 ways to calculate the Gibbs free energy change for the reaction that we're going to be dealing with. The first is negative RT ln KSP. Okay, so R is just the gas constant, T is your temperature, KSP is the solubility product. And this is why I was so hardcore about solubility products, because this whole lab centers around being able to calculate and use solubility products. So that's one way. The other way is to use the enthalpy and entropy changes in concert with the temperature. That's a second way of getting delta G. They are the same, okay? They're no different. It's the same quantity. It just, there's more than one way to calculate it. This lab has you go about this both ways. So you're going to calculate delta G using this equation and this equation. And ideally they would match, but they don't. I'll be honest and say that generally the people don't seem to get very good results for this lab. The most recent group, a couple people actually did really well, but in general they don't tend to work out very well. So I say that to say this: when you do your scatter plot for this lab, don't freak out because the straight fit is terrible, like the correlation's weak. Just roll with it. It's going to be anyway, and I'll discuss maybe why that is in a minute, but just don't freak out over it. You're not going to get a very good fit. It's not going to happen. Not with this data anyway. So, okay. The thing to understand here is that equation 1, delta G comes directly from KSP. With equation 2, it's not quite the same. Equation 2 still comes from KSP, but KSP isn't formally written in this equation. You have delta H and delta S. You have to get delta H and delta S from KSP. So even though KSP doesn't show up in this equation formally, it's still in the background because delta H and delta S both come from KSP. So to do either of these things, use either of these equations, you have to get the solubility products before you can go any further. So here's my little flow chart for this to kind of illustrate that. So method 1, again, go from KSP directly to delta G. Method 2, get KSP, then get delta H and delta S from KSP, and then you can calculate delta G from delta H and delta S. So again, I stress this, these are equivalent. It's the same thing, it's just two different ways of calculating it. One directly from KSP and one with an intermediate step here, where you have to get delta H and delta S, and only then can you get delta G. So part 1 of the spreadsheet deals with calculating the KSP. Part 2 of the spreadsheet deals with calculating delta H and delta S. And then part 3 will formally have you use these two equations to calculate your delta G's. Okay, so like this is part 1, calculate KSP, that's part 1. Part 2 is calculate delta H and delta S, and then part 3, calculating delta G, two different ways here. As far as getting delta H and delta S from the KSP, you're going to use a graphical method to do this. Okay, and I've got a crude sketch here. So what you're going to do, like I said, in part 1, you calculate your KSP values over, it's for the reaction carried out at 5 different temperatures. And you'll plot them. You're going to plot the natural log of KSP as a function of the inverse of the temperature. So it's ln of KSP as a function of 1 over T. Okay, and you should, like I said, you're going to get something that's not really much of a straight line. You'll do your straight line fit. The points are kind of all over the place. You'll do your straight line fit. Now, to get delta H and delta S from this graph, what you have to do is you have to realize, since both of these expressions are equal to the same thing, i.e. delta G, I can set these two expressions equal to one another. And that is what I have done right here. So negative RT ln of KSP equals delta H minus T delta S. Okay. Then I'm just going to go through and divide by negative RT. So that leaves me with ln of KSP on one side and all of this nonsense on the other side. Negative delta H over RT plus delta S over R. And I can carry this one step further. I can pull this T out by itself and just write this term as negative delta H over R times 1 over T. I'll leave the second term alone. I don't do anything to that. Again, these are the same. All I'm doing is pulling out the T as like a separate factor here. That results in what is basically the equation of a straight line. Because if you go up here and you do this plot and you do your straight line fit, you get an equation of the form y equals mx plus b. Okay, well, mx plus b here is going to be delta h, or negative delta h over r. That's going to be your slope. 1 over t, that's your x. Delta s over r, that's your y-intercept. That's your b value. Okay. So what this final form down here does is this allows me to say, okay, well, if m is equal to negative delta h over r, which is I've rewritten explicitly down here, if that's the case, then m times r is equal to negative delta h, or negative mr is equal to delta h. So what I can do is I can take the slope from the equation of the line up here. I can take this slope, multiply it by negative r, and that will give me delta h. Okay, similarly, b is equal to delta s over r, right, which I've written explicitly down here. So I can take the y-intercept b here and just multiply that value by r, and that gives me delta s. So what this has done is, recognizing this right here has allowed me to calculate delta h and delta s by simply drawing up a scatter plot, doing a straight line fit, and getting the equation. Once I have this equation, I just need to, again, multiply by negative r to get delta h, multiply by R to get delta S. That gives me delta H and delta S, and I can use that to get delta G that way. And that's kind of, as far as the spreadsheet goes, that's like the end goal here, is to, again, calculate these two, or these, this value two different ways. Okay, method 1, method 2. And that's really what the spreadsheet strives to do. So that's the process for doing that. As far as the actual reaction itself and how to calculate KSP, this is the reaction right here. Okay, what you would have done is taken borax, it's a compound called borax, is right here, and dissolved it in water, and it's sparingly soluble. So the solution becomes saturated very quickly, and every mole of borax that dissolves, you end up with 2 moles of sodium cations, but you also end up with a mole of triborate anion. So the idea is, for every mole of triborate in solution, that's a mole of borax that has dissolved. So if you can figure out how much triborate is in solution at a particular temperature, you can figure out how much borax has dissolved at a particular temperature. In other words, you can get the molar solubility for borax at that temperature. And once you have the molar solubility, right, you can, just like we've done 1,000 times before, you can use that with the K to get the KSP from the molar solubility here. This is that same 4x cubed expression we've dealt with 1,000 times. I go through the steps to derive it right here. This is why I've been so hardcore about solubility products, because you have to be able to see where this comes from and know the difference between solubility product and molar solubility for this to make sense. So the whole experimental portion of the lab, like what you would have actually physically done if you've been in the lab, centers around determining how much of this is in a solution at a given temperature. Because once I know that, I can calculate the solubility product at that temperature. So to do this, to figure out how much borax or triborate is present, what you would have done is you would have prepared like a borax solution at 5 different temperatures, and then you would have taken each of your samples and you would have titrated them with hydrochloric acid. And you do this because the hydrochloric acid reacts with the triborate anion. So again, up here, borax breaks apart into triborate. That triborate down here reacts with hydrochloric acid in a 2-to-1 ratio. So one mole of triborate reacts with 2 moles of hydrochloric acid. So if you have a solution with triborate anions drifting about and you titrate it with hydrochloric acid, you can figure out how much triborate is present based on how much acid it required to react completely with this. I guess what I'm trying to say is you can use the volume of acid required to determine the moles of triborate present. And like I said, once again, once you have the triborate present, you just divide by your volume and that gives you X, and then you can get KSP. So to get moles of triborate from volume of acid, I have this calculation written right here. For part 1 on the spreadsheet, column C has the milliliters of hydrochloric acid values. If you take those and multiply them by the concentration of the hydrochloric acid, that's going to give you moles of hydrochloric acid, and you can report those values in column D. If you take the moles of hydrochloric acid in column D and divide by 2, that gives you moles of triborate, and you can record those values in column E. Then to get the molar solubility, all you have to do is take the moles of triborate that you recorded in column E and divide by the volume of the sample. And for each sample, the volume is 5 milliliters. So when you go to calculate your molar solubility, you need moles per liter, right? Column E has the moles of triborate. So to get the molar solubility, all you have to do is take column E and divide that by liters of solution. So make sure you take the volume and convert it to liters, because it's, like I said, it's a 5 milliliter sample, so you need to convert that to liters. Then you can just divide column E by that volume, and that gives you the molar solubility X, which you can just report in column F. Column G is blank, and then column H, just take your column F value, cube it, multiply by 4, and that'll give you the KSP at that temperature. So once you have that series of KSP values, like I said, you can just calculate the natural logarithm, plot that as a function of the inverse of temperature, and that will allow you to get your delta H and delta S values in part 2. Then in part 3, you just calculate your Gibbs free energy changes based on the data from part 1 and part 2. Okay. After you've completed the spreadsheet, there's a series of 5 post-lab questions, so to speak. I don't care. You can type them on the spreadsheet, or you can type them on a separate sheet and just make sure you submit them one way or the other. I don't really care. If you type them on the spreadsheet, make sure you put them where I can find them, because like a couple times in the past, I've given people zeros because I didn't think they answered the questions, and they just did, but it was like all the way at the bottom of the spreadsheet. Just make sure you put them somewhere I can find them if you choose to answer the questions on the spreadsheet, but I don't really care. The first question asks you to determine whether or not KSP increases or decreases with respect to temperature. Okay, this question trips a lot of people up, and the reason that it does that is because if you look at this like my sketch of the plot, okay, oftentimes people see this downward slide here, and without really thinking about it, they say that the solubility product decreases with temperature because it's going down. And that's wrong. And it's wrong because you're not graphing temperature down here on the x-axis. You're graphing the inverse of temperature. Okay? So from left to right, as KSP decreases, the inverse of temperature is increasing. Well, if the inverse of temperature is increasing, the only way for that to happen, because the numerator here is a constant, the only way for this quantity to increase is for t to get smaller. So if the inverse is increasing from left to right, the temperature is actually decreasing from left to right. In other words, KSP is decreasing as the temperature is decreasing. Because again, 1 over T increases down here. T decreases from left to right. So ln KSP decreases from left to right. Temperature decreases from left to right. You can look at that in reverse too. You can say from right to left, the temperature is increasing, and from right to left, KSP is increasing. So, I mean, what you see here is that as the temperature increases, the KSP appears to increase as well. And a lot of people, again, they don't see that. What they see is just this going down, and they don't really stop to think about what's going on down here on the x-axis, and they say, well, it's not decreasing, it's increasing. And so that's something that you kind of have to get your head around before you can answer that question correctly. So that's question 1, and I try to put it succinctly just by saying, ln of KSP versus 1 over T scatter plot has 1 over T increasing from left to right. If 1 over T is increasing from left to right, then T increases from right to left. And you just have to ask yourself, does KSP increase or does it decrease from right to left? And that's going to tell you how the solubility product behaves as the temperature increases. Its behavior from right to left, not left to right. That's what tells you how KSP changes with temperature. Question 2 builds on question 1, and so you have to answer question 1 to be able to answer question 2. I should say though, question 2 and 3 ask your opinion. So actually what I'm doing here is I'm giving you my thought process for how I would have answered question 2. There's not really a wrong answer for question 2 or 3 because it's asking what you would have predicted. Do you predict this reaction to be endothermic? Do you predict delta S to be positive? That's up to you. I'm just kind of, so I mean, as long as you answer it, it's like you get the points for those two. There's no real wrong answer there, but I'm trying to explain how I would have gone about this. So for question 2, it's asking, would you have predicted the reaction to be endothermic or exothermic? And there's a trick that you kind of have to use to get the right answer here as far as like making the right prediction. Like I said, you can say whatever you want, but to really predict it correctly, you have to use Le Chatelier's principle to do this. The thing of it is you're going to end up using it backwards, and they don't really often teach you how to do that or to like infer things in the lecture. It's just not really how it's taught. So what I said was, if the solubility product increases from one temperature to another, okay, that indicates that the equilibrium position has shifted further to the right. If the solubility product increases, you've got more ions present in solution. That means that more borax has broken apart, more of it has dissolved. So if the solubility product is increasing from one temperature to another, then that means the equilibrium has moved further towards products, right? You're getting more products. It's driving the reaction to the right. So if an increase in the solubility product from one temperature to another drives the reaction right, and the temperature from one to another is increasing, what we can say then is that actually increasing the temperature appears to drive the reaction to the right. Because again, with increasing temperature, the KSP appears to increase. And if the KSP appears to increase, then the reaction shifting its equilibrium position to the right. So increasing temperature then shifts equilibrium to the right, or further to the right. Le Chatelier's principle talks about this, right? When you discuss temperature effects upon the equilibrium position of a reaction, Le Chatelier's principle, for an endothermic reaction, treats heat as being a reactant. And for an exothermic reaction, it treats heat as being a product. And in general, Le Chatelier's principle says, if you increase the concentration of a reactant, that shifts the equilibrium to the right. So if you're adding heat and you see the equilibrium shift to the right, that's indicative that you have an endothermic reaction here. So to tie all this together, okay, if solubility product increases with temperature, okay, that means that increase in the temperature drives the reaction further to the right. And if increase in the temperature drives the reaction's equilibrium position further to the right, then by Le Chatelier's principle, this is probably going to be an endothermic reaction. So based on the behavior here, I would have predicted the reaction to be endothermic. Because again, increasing T increases KSP, which in turn indicates the equilibrium lies further to the right. So you can say increasing T, shifts the equilibrium to the right. And that typically, indicates that heat is acting like a reactant. So by Le Chatelier's principle, that appears to be endothermic. So I would have predicted the reaction to be endothermic. I always give one or more questions on the final, basically going through what I just did. I ask, do you expect the reaction to be endothermic or exothermic? Like I said, for the post lab here, there's no real right or wrong answer because you've not done this before, and so, it's a guessing game. For the final, I like expect you to be able to go through this sequence of like steps, this thought process, and answer correctly whether you would predict it to be endo or exothermic. I have multiple questions that test that, like scatter plots, where you have to figure that out. So make sure you understand why I'm predicting it's endothermic, and make sure you can understand the argument for the opposite case. Like, what if the reaction's exothermic? How would you expect the solubility product to change with respect to temperature if the reaction is exothermic instead? Either one of those questions are fair game, endo or exothermic for the final. Either one of those are fair game. I have scatter plots for both, and this is the kind of stuff right here, this reasoning that you're occasionally asked to do in organic and biochemistry. Like, there's no computation here. You're looking just at a graph, really, and being asked to predict the effects, that temperature changes might have. But this thought process, these types of questions do show up from time to time in those courses, so it's really important to make sure that you're comfortable with my thought process here and how I answered 1 and 2 together. Number 3 is simple. It just asks, would you expect the delta S value to be positive or negative? Dissolution increases disorder, okay? And you're dissolving here. In general, when you take something and you spread it over a larger volume, that increases the disorder. And so I would expect the entropy to increase. In other words, I would expect delta S to be positive. Okay, so that's all you really have to do to answer that question. Dissolution tends to increase disorder, right? That's how you can remember that. Dissolution increases disorder. An increase in disorder is an increase in the entropy, and so dissolution probably corresponds to a delta S value in general. Question 4 asks whether at this particular temperature, whether or not you would expect the reaction to be spontaneous. And so, all you really need to do is, I think it asks at 298 K, and you don't have that. So what I just tell people to do is look at the closest temperature, which is like 300. It's not far off the mark. Just look at it. Is delta G positive or negative? If delta G for 300 is negative, then you would expect it to be spontaneous at this temperature. If delta G is positive, then you would not expect it to be, spontaneous. You would say it's non-spontaneous at this temperature. It's not a deep question. You just need to look at delta G and figure out whether it's positive or negative. And my notes for 4 really probably should have been included under 5. I probably should have just left 4 blank. This is kind of all one thing. Question 5 asks if the reaction is not spontaneous at this temperature. So if it's not spontaneous at 298 K, if you run through these calculations and you get a positive delta G for 298 K, or like I said, 300 K is what we're going to use, but it asks if it's not spontaneous, it's non-spontaneous at this temperature, is there some temperature for which you would expect that to change? In other words, is there some range of temperatures where the reaction could be spontaneous? It may not be spontaneous at 298, but is there some other temperature that it might be spontaneous at, or might be spontaneous above or below or whatever? In general, there are like 4 cases, and you can find this online. Like it's easy to find the chart that illustrates this a little bit better, but in general there are 4 cases. Okay, so if you go back here and you look at the equation that I had here, delta H minus T delta S. You can see that, like, if delta H is really big and delta S is really small and T is not really large, if delta H is positive, you're only going to subtract a little bit from that if these values are small. So for a very large delta H, if this is positive, this is going to be positive, unless this overtakes this. And this would have to be enormous if you've got a large delta H. This would have to be huge to overtake that and make this thing negative, okay? So what I'm getting at here is if T were really large, like if you carried out a reaction at a really high temperature, this quantity here could be a lot bigger than this. And so subtracting this from this would give you a negative value. For lower T, however, there's probably just not enough here to subtract from this and get a negative number. Delta H is too large and too positive, so you still end up with a positive delta G. In other words, it would be non-spontaneous. My point being, the signs, the algebraic signs on delta H and delta S kind of determine the ranges, if any, over which delta G is going to be negative. In other words, the ranges over which the reaction may or may not be spontaneous. Okay? So, if delta S is positive, delta H is positive, you're going to get a delta G only at sufficiently high temperatures. If delta S is negative and delta H is negative, you're only going to get a spontaneous reaction to occur at low temperatures. If you've got positive delta S and negative delta H, it's going to be spontaneous everywhere. And if the opposite is the case, then it's not going to be spontaneous at any temperature. So, okay, based on that, I just realized I forgot my fraction bar. Wow. Okay. So question 5, again, it's asking you, like, is there a range of temperatures you would expect the reaction to be spontaneous at? Well, if you ended up getting a negative delta S and a positive delta H, then the answer would be no, there is no range. If, on the other hand, you got a positive delta S and a negative delta H, again, there, it would be spontaneous everywhere. It's these two cases right here that you can't make like a blanket statement, right? It's going to be, for case 1, it's spontaneous only at sufficiently high temperatures. For case 2, it's spontaneous only at sufficiently low temperatures. And so for these two cases, you kind of have to look and see if you can determine a threshold, right, where it changes from like non-spontaneous to being spontaneous. And that's basically what I walk you through here in question 5. So I said for case 1, which is this one up here, okay, reaction becomes spontaneous at suitably high temperatures. You need to determine the temperature above which the reaction becomes spontaneous. Okay, so there's some temperature at which that T delta S quantity is larger in magnitude than delta H. So when you subtract T delta S from delta H, you get a negative value. And that's what I've tried to illustrate here. So if you set delta G equal to 0, and then you use the equation for delta G, delta H minus T delta S equals 0, right? What you can do is solve this equation for T. And if you do that, what you'll find is that delta G equals 0 when T is equal to the ratio of delta H to delta S. And I emphasize for positive delta S and negative delta H. This conditional here is really important. You can't always assume that. I forgot to mention that when I did this back over the summer, and that caused people some confusion. So this is not always valid. It is valid under these conditions. Okay, so again, what I'm saying is at this temperature, delta H divided by delta S, that means delta G is 0. And for this particular case, we know that at high temperatures, the reaction is going to be spontaneous. So this is the temperature at delta G is 0 for. That means that temperatures above this temperature should yield a spontaneous reaction because, again, it's suitably high temperatures, right? We're basically determining the 0 point. Anything above that is going to be spontaneous. So that's how you determine that temperature. So above T here, you should get a spontaneous spontaneous reaction. And those are the post-lab questions, like I said. So you've got a data sheet with 3 parts. The first part is calculating KSP values. The second part is calculating delta H and delta S using a scatter plot. And the third is calculating delta G 2 different ways. Once you've done that, you can answer the 5 analysis questions. Again, 1 and 2 together are just like really important for people going on. And so I can't stress enough to make sure that you understand the thought process there. And it will show up on the final. I always put those types of questions on the final. So that's about it. I've changed things a little bit from the summer to try and make it a little bit less confusing. If there's something not clear or missing, let me know, because you guys are working on spreadsheets a little bit different than what I used back in the summer. Again, it was to try and streamline things a little bit. So if there's something that's missing or something that's not clear, let me know so I can send out a correction and fix it. So